So, yes, my name is Ina, and today I would like to talk about the work that I conducted while I was employed at the Helmholtz-Zentrum Herion in northern Germany. This work brought together experts from different fields, which I have listed here. So, Ralf Weisse and Oliver Krüger are colleagues from the Herion. Jens Möller is from the German Federal Maritime and Hydrographic Agency, the agency who made the measurement data available, and he contributed with a lot of interesting ideas. And then Sander Wals and Markus Brühl are colleagues from the Technical University in Delft. They are experts on nonlinear wave equations. I am now working at the Federal Waterways Engineering and Research Institute in northern Germany, and I've switched my focus from ocean waves to ship generated waves. But today I would like to speak about rogue waves and the question, are they really unexplainable? I would like to show you first why it's important and also quite interesting to study rogue waves. We spent 5 years on these rogue wave studies. And first, we analyzed a lot of measurements off the German coast. We asked the question how common rogue waves actually are. And after we had gotten an impression on how often they actually occur, we searched for explanations for rogue waves. Wave behavior is different in deep and in shallow water, um, which is why I have split this up into two topics. And then I will show you what we found and draw some conclusions. Now I would like to show some examples of rogue waves. And because it's difficult to be there in the ocean, just in the instance when a rogue wave passes and then actually record it, I am showing some simulations. I did not do the simulation myself. I found it in the literature. This is based on a particle-based method, and I think it shows quite well what it looks like when a huge rogue wave approaches an offshore platform. Here you can see the rogue wave approaching from the left side, and after a few seconds, it has already almost passed this platform, and it does a lot of damage to it. As you can see, it moves the platform and it drags it with it, so you can see that there's a lot of force behind this huge water body here. And those platforms are constructed with an air gap to the sea surface that actually huge waves cannot reach up to the platform, but in some cases it actually happens. This is an example of a 30-meter high wave, and that's actually realistic, for example, for the northern North Sea. If you now imagine you have your cabin somewhere up here, this is something you really don't want to experience. I have another example from a cargo ship that experienced a rogue wave off the coast of South Africa in the Agulhas Current, and you can see how dangerous this actually is. Here is another example from a more everyday situation. A wind farm support vessel would go out to the wind farms to supply them, for example, only on calm days when they expect the water surface to be calm. But imagine you are on this ship and you want to board the platform, and just in that instant, you will experience a wave that is 2 or 3 meters high and comes all of a sudden. This will also create a very dangerous situation. So from these examples, we can learn something about the nature of rogue waves. They appear unexpectedly and they may develop strong forces. One of our research questions was, why do rogue waves occur? Because this explanation is the precondition for prediction. And the prediction of rogue wave is actually the ultimate aim when we study rogue waves. Now, I've used the term rogue waves already quite a lot of times. Some people also call it freak wave. But what is it actually? In order to explain this, we need a time series like this one. This was measured during our studies in the North Sea. On the x-axis, you have the time, and on the y-axis, you can see the elevation of the water surface. In order to find out whether this large wave in the middle of the sample is a rogue wave, we first need the significant wave height, which is drawn here. This is the mean height of the highest third of waves in the sample. And then we need the individual height of this one wave in the sample. And the definition of a rogue wave is quite simple. If this wave is at least twice as high as the significant wave height, we can call it a rogue wave. Please note that this is a relative definition. So a rogue wave is a wave that is exceptionally high with respect to the surrounding sea state. And in the southern North Sea, where we have most of the time significant wave heights around 1 meter, this would mean that already a wave of 2 meters high would classify as a rogue wave, although it may not harm people or structures in that case. But for statistical reason, we also analyzed these rogue waves, all of them that were in our data set. If we remember now that the explanation of why rogue waves occur is a precondition for their prediction, I have added another box here. The first question, how often do they occur? Because we need to know how often we actually see them in order to ask where do they come from. So we need to know what it is that we want to explain. Theoretically, wave heights in the ocean follow a distribution, for example, a Rayleigh distribution. Here you have on the x-axis the wave height, and on the y-axis, it's the probability density function. So this function shows us that low waves with a small wave height occur very often. And then here, this white part below the curve, that's the highest third of samples, the one we need for the definition of the significant wave height. And the higher the waves become, the lower is the probability that we will actually have them in our data set. The waves that we are interested in are twice the significant wave height. So rogue waves, they are at the very edge of this distribution. And our question is, are rogue waves part of these general wave height distributions, or do they follow their own distribution? What we already know about rogue waves today, we know that they occur more often than previously expected. In earlier times, rogue wave occurrences were based on what seafarers told, for example, and many times they were not even believed. But this is a more present study from 2011 till 2018. Um, Rogue waves that were collected from different sources, and all of these rogue waves were associated with accidents. So those are actually very large rogue waves. And from that map, you can see that rogue waves can occur all over the world. And here in places where that are sparsely populated or where there is not so much marine traffic, there are not so many reports, but in all other places, you can actually encounter rogue waves. Rogue waves can also be generated in the lab based on a mechanism that is called dispersive focusing. This is basically the superposition of waves. Long waves overtake short waves and they may add up on top of them. So we can see this here. This is measurements from a wave tank in Hanover. And the scientists there sent out a wave package. And here you also have a time on the x-axis. So they sent out small waves first, followed by larger and longer waves. And this is at the beginning of the tank, 3.6 meters. If we go along the tank at 50 meters, you can see that some of the larger waves have already overtaken the smaller waves and just summed up, added up on top of them. And if you go further down the tank at 60 meters, you can see that several waves have added up to form this large rogue wave. In pictures, it looks like this. Here we see the tank and they send the wave package down there. And here at 70 meters, the waves have summed up to form a large rogue wave. You can also do this with waves from different direction. This is a circular wave tank in Edinburgh, and they have wave paddles all around, so they are able to send waves from different directions and have them add up, superpose, for example, in the middle of the tank to create a rogue wave there. So it's definitely possible to create rogue waves based on linear superposition. The question is, does this explain all rogue waves that we see, for example, in measurement data? Our measurement data is from the North Sea. We can see a map here. Up there is Scandinavia. Here is Great Britain. And then we have here Germany. And on the next slide, I will show only a part of the North Sea, the southern part, the one in this red box. That's here. So Germany is here, there's Denmark, the Netherlands, and over there is Great Britain. This map shows where our measurement positions or our measurement instruments were located. At all these yellow dots, we had wave buoys. They look like this. They float on the sea surface. They have an antenna to send their data to the shore. And if you take a section through this or yeah to the sea floor, you can see that they are anchored to the sea bottom with a heavy chain, so they cannot leave their position. But due to this flexible rubber band in the anchoring, they are able to move with the sea surface. And then at the sampling frequency, they tell us at each time instance where they are right now, and from that we can reconstruct the movement of the water surface. At these red boxes, we had wave radars. They look like this. They are fixed to offshore platforms. They cannot move, and they look down and measure the distance to the sea surface. Both of those instruments have in common that they give us time series like this one. And this is zoomed in, so actually each time series was 30 minutes long. After that, after we had the time series, we discarded all the erroneous data. And then after that, we were left with a sample or with a data set of 1 million waves. And in these waves, we then basically counted the rogue waves and we made our statistical plots. So what we did was, first of all, comparison with the common wave height distributions. We have already seen the Rayleigh distribution on an earlier slide. This is also the Rayleigh distribution, just in a different representation. It's cumulative. So this plot tells us the probability that a certain wave height is exceeded. The Rayleigh distribution is a special version of the Weibull distribution. And how to read this plot? For example, the probability that the wave height of 0 is exceeded is 100%, which makes sense because no wave in our dataset is smaller than 0. The waves that we are interested in are 2 times the significant wave height. And if we now check the Rayleigh distribution, we can read that 1 in 3,000 waves is expected to be a rogue wave. In 1978, Forrestal made some measurements in the Gulf of Mexico during a hurricane and found out that the Rayleigh distribution is actually too theoretical, and in the real ocean, the large waves will not occur as often. So Forrestal added some new parameters to the Weibull distribution. This is what we see here, the black line. If we read from the Forrestal distribution, we would expect 1 in 6,000 waves to be a rogue wave. Now let's compare this to our data from the dataset. We see here a yellow line and an orange line, and both of those are data from one of the wave buoys each. And we can see that they compare very closely with the Forrestal distribution. They follow it very closely, except maybe for up here, but this is not as reliable because this is based on very, very few data points. For the radar instruments, this actually looks a little bit different. That's those two red lines, the red one and the dark red one. They also follow the Forrestal distribution closely up to maybe where rogue waves start, and then they start to deviate from this distribution. So we are asking the question, what's going on up here? We want to look at this closer. Now we have already seen that our results, statistical results, strongly depend on the choice of measurement instrument. We had those two different instruments, the wave buoys, and they actually tend to underestimate wave crests. You can imagine that because they slide on the water surface, they may slide away from large crests, or they get even dragged through the crests. And also they have their own Lagrangian motion. This means they move like a water particle with the water surface in a circle. And then they move with the first wave, and while they are still coming back to their original position, it might happen that a large wave crest just moves over them and they miss this wave crest. And also it's part of an anchored system. So if simply the anchored chain is not long enough, the wave buoy will not be able to follow the highest waves. And on the other hand, we had these wave radars that were fixed and measured the distance to the sea surface. They may overestimate the rogue waves because they may interpret spray or fog because they think that this is already the sea surface. And also, they might interfere with the platform and measure something that's not really a wave, but part of the structure. And then there is another problem associated with those different measurement instruments. They had a different sampling frequency. So the wave buoy measured at 1.28 hertz, and the radars measured at 2 or even at 4 hertz. I would like to illustrate this problem using a time series again. This one was measured at 2 hertz. So everywhere where they are red points, we had data. So this is a wave crest that was measured, and this is the wave trough. And this wave classified as a rogue wave. If this wave, though, had been measured at 1 hertz only, so now here it's subsampled, you can see that we missed the crest and we also missed the trough. So if before this wave was 2.04 times the significant wave height, measured at 1 hertz, it may only be 1.99 times the significant wave height and thus not classify as a rogue wave anymore. So a lower sampling rate means that fewer rogue waves are detected. And this is usually the difference between wave buoys and wave radars. We also see this when we compare our results from the different stations. Here we have again in yellow bars obtained from wave buoys and in red bars obtained from radar devices. And here, this black line is the expectation of how many waves will be rogue waves according to the Forrestal distribution. And as I showed before, this is the expectation of 1 in 6,000 waves. Most wave buoys identified fewer rogue waves, while most radar stations identified more. And there is one exception. It's this wave buoy, it's called Z. And for the radar station, this station found most rogue waves, and those two stations have in common that they are located in shallow water. We will talk about shallow water waves a bit later. Now, another question that we asked in the beginning of our studies, are there differences between seasons? Because it seems intuitive that more rogue waves should occur in winter when there are more storms. Now let's have a look at the full data set again. Here we simply counted how many rogue waves did we found in which month. And then surprisingly, most rogue waves occurred in July and August, which in Germany is summer. Then we had a look at how many waves do we have in total. It's that green line. And we found that most waves occurred in summer. And that actually makes sense because in summer, when you don't have that many storms, you have small waves and you have short waves, so you get a lot of them. So, what we did to relate this, we divided these gray bars by the green line and we got the relative number of rogue waves. So, how many waves of all of those that we have measured are actually rogue? And this is the relative number of rogue waves throughout the year, and it's quite constant. So the result is that there is no seasonality to rogue waves. Now I would like to draw a conclusion for the statistics part of the work. We have seen that rogue waves are not that uncommon. Rather, in this data set, rogue waves larger than twice the significant wave height seem to be part of the general wave distribution, and they occur just as often as expected, which we have seen here for the 2 times the significant wave height. But still, there is a question what's going on up here for waves that are larger than 2.5 times the significant wave height. Is it possible that nonlinear processes play a role for these additional rogue waves that we did not expect? Nonlinear processes are different in deep water and in shallow water. To give you just an overview, in deep water, the so-called modulational instability is suspected to play a role for the formation of rogue waves. The modulational instability works like this. If you have an initial wave train with some frequency and you perturb it with a frequency that is very close to the initial frequency, then your wave train will disintegrate into groups. And if you observe this for a while, you will observe the growth of one wave in the group at the expense of the other waves. This is something that only happens in deep water. In shallow water, this is not possible because shallow water waves are not dispersive. In shallow water, we instead have another nonlinear phenomenon that is called solitons. Solitons are solitary waves that travel um, at the same speed without changing their speed or without changing their shape while they propagate. I would like to focus on deep water rogue waves first and on the question, is it possible that rogue waves in our data set were generated by a modulational instability? Here you see the modulational instability again. We can now follow again waves in a wave tank. We have here the initial wave train, which is slightly perturbed. And if you go along the tank, here it's 2.25 meters. And then you go further down the tank and you see how one of these waves evolves at the costs of the surrounding waves. So this is a nonlinear exchange of energy. Um, in order for this to happen, you need quite some nonlinearity in your data. And to measure the nonlinearity of the sea state, we use the parameter Benjamin Fear index, which is the steepness of the waves divided by the frequency bandwidth. The BFI becomes high if you have a low frequency bandwidth, and that means that most frequencies in your sea state are very similar. So the frequency band is small, we call that. So now we checked whether in our data the preconditions for a modulational instability are given. The first precondition is deep water. And although our data were taken at maximum at 30 meters water depth, the water depth or deep water in terms of the modulational instability is a relative definition. So it's the wave number times the water depth must be larger than 1.36. And this was given for a lot of waves in our data set. Then the second precondition is a narrow spectrum in frequency and direction. This is the directional spectrum of the waves in our data set, typical for the southern North Sea. And here you can see how the waves distribute over the frequency, this is the radial axis, and over the direction. What we call spectral bandwidth is this distribution in frequency direction, and the directional spread is the distribution over the directions. If you have a very narrow sea state, your sea would look like this. This is a typical swell. So the waves are very long. Most of them come from the same direction, and the frequencies are very similar to each other. Whereas if you have a broad sea state, you will have waves of different lengths approaching from different directions and then superposing to a quite chaotic sea state. Now let's have a look at our data again. We can take all of our samples, and for each sample, we performed a Fourier transformation and then got this linear FFT spectrum. So on the x-axis, you get the frequency, and on the y-axis, the power spectral density. And here you can see how the energy of the waves in the sea state is distributed over the frequency. If we now want to know our frequency bandwidth, we can use the broadness parameter to evaluate this. That can be calculated by means of the spectral moments, Mn. The spectral moment M0 is the area below this curve. The spectral moment M2 is the standard deviation of the data here. And M4 is the kurtosis, so the peakedness of our spectrum. So what we did now was to compare our broadness parameter for those time series in which we saw a rogue wave to those time series in which we did not have a rogue wave. And because we had a huge sampling bias, meaning that most of our samples, of course, did not include any rogue waves, we did some bootstrapping for the samples without rogue waves, and that's why you can see a distribution here for the normal or non-rogue wave samples. The thick red line is the rogue wave samples, and we actually found a difference. So the C was slightly less broad at time instances where we measured a rogue wave. The problem was that this difference could be detected statistically, but it was actually not useful for a prediction because the differences were very small. And in general, our C states were quite broad. What does this mean for the BFI? This measure for nonlinearity of the C state. If we have a broad frequency distribution, it means that the BFI also usually is quite small. A BFI of much, much less than 1, so close to 0, means that our full C state can be described by linear superposition, while a BFI larger than 1 would say that nonlinear interactions are expected to dominate the wave evolution. And here you can see that the BFI is quite low, and also that there was no detectable difference between rogue wave time series and non-rogue wave time series. So what about the directional spread, which is more intuitive just to read? Here we can see that our directional spread is quite broad as well. And also here we could not detect any difference between samples that included rogue waves and samples that did not include rogue waves. So for our deep water rogue waves, we can draw the conclusion that according to the values for bandwidth, BFI, and directional spreading, the modulational instability is not a likely mechanism to occur in our North Sea dataset. So probably most deep water rogue waves in our set were generated by dispersive focusing, that is the superposition of different waves. Let us now proceed to shallow water rogue waves, in which the modulational instability does not play a role, but instead another phenomenon that is called soliton. In order to assess this topic, we need some shallow water wave theory. Wave evolution in shallow water is guided or described by the KdV equation. The KdV equation includes a parameter called U, which is a measured time series, and it includes spatial derivatives, that's x, and time derivatives, that's t. And also we have some factors here, c and alpha and beta, and those are solely dependent on gravity and on the water depth. And since we are looking at one station now only, these are constant factors. The KdV equation is an evolution equation, which means, quite fascinatingly, that it tells us what our measured time series will look like if we let it evolve in time and in space. Now, we use this method the following way. We put our time series into the KdV equation, and then we solve this equation by something called the inverse scattering transform. This is in some way a nonlinear Fourier transformation because, similarly to the Fourier transformation in the linear case, it transfers our time series into a different domain. In the nonlinear case, we get two types of spectra. One is the continuous spectrum, which I will not explain any further, and I also did not use any further. And on the other hand, the nonlinear soliton spectrum. And this was something we were interested in. When you solve this as a complex eigenvalue problem, you will find solitons at each of the complex eigenvalues. Translated to the real world, this would mean that the nonlinear continuous spectrum describes all the oscillatory waves that are part of the time series, and the soliton spectrum describes solitary waves that are hidden in the time series. Each solitary wave with its individual amplitude And important to remember that these always interact, the solitons and the oscillatory waves. And it's not easy to see solitons in the time series. You would need this spectral method to make them visible in a spectrum like this. But how can we now associate these solitons with rogue waves? This is the time series that we had before, just that now I'm showing the full 30 minutes. Here is the rogue wave at approximately 800 seconds that we have seen before. So we performed the inverse scattering transform and get this soliton spectrum, just the one from the slide before. Now I will zoom into this blue box so you can see the rogue wave better. It's here. And what we did was simply to reduce the height of this one original rogue wave to 80% of its original height. And then we did the nonlinear Fourier transformation again. We got a new soliton spectrum, and we discovered that this large soliton from the original spectrum had moved to had become smaller now. And also there were some minor changes within the spectrum down here. And this was only initiated by changing the height of this rogue wave. We changed nothing else in the time series. So these solitons that have changed in the spectrum must be associated with this rogue wave and play some role in the formation of the rogue wave. I would like you to note that this highest soliton here that is associated with the rogue wave is only 1.5 meters high, while the crest height of the rogue wave is 3 meters. Sorry, I switched already. So it's not enough to take only the soliton to explain the rogue wave. They are not interchangeable. The solitons also need an interaction with the oscillatory waves to explain the full height of the rogue wave. So for shallow water, we can draw the following conclusion. Nonlinear processes play a role for shallow water rogue waves in this data set. Rogue waves are probably a result of the interaction of solitons with oscillatory waves. Now I would like to sum up the insights that we gained in the course of our rogue wave studies. Before I will try to estimate whether the prediction of rogue waves will be possible someday. First of all, we had the statistical part, and we found that according to this data set, most rogue waves seem to be rare realizations of typical wave distributions. For the deep water rogue waves, we could say that they were probably not generated by a modulational instability, at least not in this data set. And however, nonlinear processes were important for shallow water rogue waves in this data set. The shallow water rogue waves are probably a result of the interaction of solitons with oscillatory waves. Now I have prepared a few slides about our efforts into the prediction of rogue waves. Because as I said in the beginning, this is the main aim when we are trying to find out where rogue waves come from, that we want to predict them someday. Our first effort was we aimed at forecasting rogue waves based on the distribution of wave heights in the background field of rogue waves. We see here a table where we tried based on 10,000 time series to predict whether a rogue wave will occur or not. And in that context, I would like to point out the problem of sampling bias again, because naturally the population of normal waves or non-rogue waves is much larger than the population of rogue waves. That's what makes them so special. So if we look at this table, the left column shows in how many cases we observed a rogue wave. And that's the box A plus box C. So this is the total number of rogue wave samples that we had. That was 683 rogues, while the sample size of those in which no rogue wave was present is of course much higher. So this is a problem for the prediction. You can read this table the following way. The letter A stands for hits, which means we forecasted, yes, there will be a rogue wave, and there was actually one. This worked in 373 cases. But we sometimes also said, yes, a rogue wave will occur, but it didn't. And this happened in a lot of more cases because there are so many more cases that do not have a rogue wave. Then sometimes we said, no, a rogue wave will not occur, but it did. That's C, that's misses. And misses is not so much fewer than actually hits. So this is very difficult to predict. And in many cases, we said no rogue wave will occur, and that was actually true. Um, so this effort was not that useful in the end for prediction, because especially in the case of dangerous large waves, you should ask yourself what is actually worst. If you give false alarms all the time and you predict rogue waves that do not occur until nobody believes you anymore, and in the end, then you will get a rogue wave? Or is it worse to have misses, to predict no all the time, but then you will miss the rogue waves? Of course, if you always say no rogue wave will occur, you will be right most of the time, but then you miss the important cases. We tried to do the same type of prediction in shallow water after we had learned about the connection between solitons and rogue waves. And this worked actually much better. If we got an outstanding soliton in the spectrum, we said yes, a rogue wave will occur. And in in this case, in 700 cases approximately, this was actually true. And our misses were much fewer than on the last attempt, but still we had a lot of false alarms, and we had quite a few misses as well. So although here again we have a statistical possibility to predict rogue waves, it's difficult for the actual practical use because we have too many misses and too many false alarms. Then we had a look at different parameters that can be expected to alter in the vicinity of a rogue wave. For example, wave steepness. We know that rogue waves are very steep waves. So we were wondering if the waves just before and just after the rogue waves are also very steep waves. The steepness can be calculated easily from our dataset. It's defined as the wave height divided by the wavelength. And the wave height we could measure. And then we had also the wave period. And through the dispersion relation, we could then calculate the wavelength. So steepness was easy to calculate for each wave in our whole dataset. So we had 1 million steepnesses. And then we tried to look at each rogue wave that's at time instance 0, and we saw, okay, they are very steep compared to normal waves. Then we went 10 waves back and we checked if we go 10 waves ahead of a rogue wave, when will the steepness start to increase? And the wave 10 waves before the rogue wave and 9 and 8 and 7, still all the time the steepness is very low, and only one wave ahead of the rogue wave, the steepness begins to increase. So here again, the result is um, there is a difference between those waves, but it's not very helpful. Because if you warn only one wave ahead, you would call at sea and say, okay, the steepness is increasing now, the next wave will be a rogue wave. The people at sea will probably tell you, yes, I can see the rogue wave already myself. So this is not actually prediction. And then we wanted to have a look at a larger collection of parameters at the same time. And we were here inspired by a paper by Häfner et al., which is called Real World Rogue Wave Probabilities. They used a machine learning technique to predict rogue waves, and they found some important parameters that play a role in their formation. So, inspired by them, we also moved a 30-minute time window from one wave to the next for each wave in our dataset. And then for this 30-minute time window, we calculated or collected all the available parameters. And then for each wave from these parameters, we used a random forest model to predict the maximum expected wave height in the upcoming 10-minute time window. I've seen the agenda of your machine learning sessions, and I'm well aware that I'm in no position to explain anything on machine learning to you. What we have done here is very basic, and I will probably not even be able to answer any detailed questions. But we used a method called forest guided clustering, which is an explainability method for random forest models. It's well suited for problems in which features are correlated, which we often have when we look at sea states. If you want to know more about this method, you are invited to have a look at this link. So the result of the forest guided clustering method is a number of clusters with features that follow similar decision paths in the random forest model. Um, and in our case, we got 2 clusters as a result. And here you see a list of the parameters that we put into the random forest. And on top, you see the target. The target is h over hs. So h over hs equal to 2 is rogue waves. They are at this yellow end, and very low waves are at the blue end. In principle, the algorithm worked well, and we found out which parameters play a major role for obtaining the target. So here you have the most important parameter, which is the relative water depth, which makes sense because we talked about this before. Rogue waves in deep water and in shallow water are generated differently. Then we can see here the wave period and the wavelength, which are directly correlated. And the algorithm discovered this, and they behave exactly the same way in these 2 clusters. The cell number tells us something about nonlinearity of the sea state, so it also makes sense that this is different for the 2 clusters. And nu is the frequency bandwidth. And we also spoke about that before, that this may have an important influence on the generation of rogue waves. Our problem was, though, that we had expected the target in the 2 clusters to split. So we had hoped for only yellow values here, so high waves, and only blue values here. But the algorithm put the lowest waves together with the highest waves into this cluster and the intermediate waves into this cluster. So although the algorithm worked in principle, the target was not clearly distinguished, and we were not able to use this result actually for prediction. So this brings me to the rather discouraging conclusion for the topic of prediction. We are not quite there yet. So my overall conclusion, I've come to the end now, is that rogue waves, coming back to the first question, rogue waves are not unexplainable. We found several different mechanisms that can generate rogue waves, and we could even find some of them in our data set. However, they are still unpredictable. At least that's at this moment what I can say. Maybe other scientists have come further by now. I know that there has been a lot of research going on rogue waves related to machine learning. There are some publications from this year and last year. So maybe there is hope to predict rogue waves using machine learning soon. But according to our study, after that, we were not there yet. If you want to know more about rogue waves, you can have a look at these references. These are the ones I used in my talk, or you can simply ask your professor, Francesco Fedele, because he's also an expert on rogue waves. So with that, I would like to thank you. Are you still there?
Udina, very good talk. So let's start the question session. So if our friends from the internet or from they are in the virtually, do you have questions for Ina? Domenico?
Yeah,
Yes.
can I ask something real quick? Yes. So in the part about the deep water rogue waves, so there was this distribution. It was basically a spectral density, and you said that when the tail is long enough, it means that there are nonlinear processes involved. So what determines whether the waves build up linearly or non-linearly?
I would say it's the type of sea state that determines this. I think my suggestion is that we did not see those nonlinear processes in deep water in our data set, because in the North Sea, you generally have a young sea state. So the evolution of the waves there is directly linked to the wind. And probably in other parts where you have a long fetch, for example, in the Pacific, where you then get long swell waves that come from one direction, it's more probable to get these nonlinear mechanisms in deep water, because then you have a very low frequency spread and you have a small directional spread. They all come from one direction. And maybe if you then get a young sea state from the side and you get a crossing sea where those two wave systems can be separated clearly, I think then the chances are higher to get nonlinear mechanisms.
Okay, thank you.
So I see two new visitors here, Jens Moller and Harsh Desai. Can you please introduce yourself? So you also do research in rogue waves? You can also share your video so we can see you.
Yeah, hello, can you hear me?
You're my student. Okay, hi.
Yes, yes, yes. I wasn't able to attend in person today, so I joined via the internet.
Okay, thank you. What about Jens Moller? Jens Moller, BSH? Hi.
Francesco, can you see the chat? I just saw that Jens was writing in the chat that he's sorry his microphone is not working.
Oh, okay.
But maybe I can help, because Jens Möller is from the Federal Maritime Agency.
Okay.
Hamburg.
Oh, just okay.
Yeah, and he contributed to the papers and also to the ideas during our rogue wave research project.
Okay, thank you very much. So what about here, Matt?
Yeah, I had a question. So when it comes to predicting wave heights, or if rogue wave is going to happen soon, I guess disregarding rogue waves, how well can you predict just ordinary ocean waves, say 10 waves into the future? Is there kind of an intrinsic timescale where predictability in general completely fails for these systems?
In general, it's easier to predict a sea state, so a mean value of a parameter. It's easier, for example, to predict significant wave height. This can be done. I know that it's done by some researchers, also based on numerical models, for example, or on wave hindcasts. It's just very difficult to predict a single wave, and that's a contradiction, because that's actually what we want, because rogue waves are single dangerous waves, and we actually want to predict this one wave, and it does not help us too much to predict a spectrum, although it's easier to predict a spectrum. But I think actually that's also a good idea, and something that would be helpful, for example, for the wind energy industry, if they have their wind supply vessels that go out only when the weather is good. Maybe it would be useful to give them at least some time windows in which the water will be calm and they can do their work.
Okay, other questions? Okay, Ina, thank you very much. So there is another class here because we gotta go and do the IE group study, and they're waiting for the pizza. So I
Yes, enjoy.
stop here actually, and I'll